Sometimes when we get several candidate structures in the end, we can eliminate some of them by looking at the electronegativities of the atoms that are inside the structure. This is an example of that. There's another one on your worksheet. OCN minus is the cyanate ion that is on your polyatomic ion list. Let's do its Lewis structure. Now if somebody writes down an ion like this, they are giving us a hint about what the skeleton structure looks like. It's got an O on one end and an N on the other, with the C in the middle. So let's write down the skeleton structure that way. Step 2. Find the number of valence electrons. Okay, from the periodic table, oxygen has 6, carbon has 4, nitrogen has 5. Am I missing anything? You should say yes. You are missing something because you're forgetting the charge over here. You have to add another electron on for that. So you've got 16 total electrons. If I would have forgotten the charge, I would have gotten 15 electrons. That's an odd number, so I would have been thinking this was a free radical. When you get an odd number of electrons, double check and make sure that you're not forgetting the charge over here in this step 2. Step 3, connect the structure. Okay, here's my skeleton. Gonna connect it by drawing a bond between the central atom and all of the outside ones. Every bond that I draw is going to cost me 2 electrons, so I just took away 4 electrons. I've got 12 left. Step 4, satisfy the outside atoms. That's the oxygen and the nitrogen in this case. Each of those atoms wants an octet. And the oxygen has already got 2. It needs 6 more. Let's give it to it. 1, 2, 3, 4, 5, 6. The nitrogen wants 8, and it's got 2, so it wants 6 more. 7, 8, 9, 10, 11, 12. So in this step, I took away all my remaining electrons. There are no electrons in step 5 to dump. So I basically have this, just copying this over down here at this point. Is the central atom satisfied? You're going to say no, right? It doesn't have an octet, and it wants one. So I can share lone pairs with the neighbors to give it an octet. Now there are several different ways that I can do this. If I share 2 lone pairs off of the oxygen, put one there and one there, I am going to get a structure that looks like this. Everything in this structure has got an octet, so that looks nice. How about if I take one lone pair from here and share it, and one lone pair from here and share it? Then I'm going to get another structure that looks like this. So I take this one and put it down as a bond. So I'm going to make a double bond there, and I'm going to take this one down and put it as a bond. So I'm making a double bond there. Okay, so that's another structure that I can have. But what if I take a lone pair from here and a lone pair from here and I get this? There are 3 possible structures that I can get from the recipe here. Now, in order to see if I can cross any of them out, I'm going to assign formal charges. If the formal charges come out to be equivalent in all three of these, same formal charges just moved around, then I would say I had resonance. But we're going to see that they all come out to be different. And we're going to end up with just one structure instead of three. Okay, let's do formal charges here. Oxygen has got 6 on the periodic table, minus 1, 2, 3 sticks and 2 dots is 5 sticks and dots. So it's got a +1 formal charge on that oxygen. How about this carbon? Let's see, it's got 4 valence electrons on the periodic table, minus 1, 2, 3, 4 sticks is 0. And how about this nitrogen? It's got 5 valence electrons on the periodic table, minus 1, 2, 3, 4, 5, 6, 7 sticks and dots, which is a -2 charge. Okay, now if I look at this structure right away, I can see that there's kind of a high formal charge on this nitrogen. And what's more, there's a positive formal charge on the oxygen. Now, oxygen is a very electronegative atom. When I say electronegative, do you know what I'm talking about? It means electron greediness. And generally, electronegativity increases when you're going across like this. In fact, the fluorine has got the highest electronegativity of any element. We don't form compounds out of these usually, so we don't look at that when we're considering electronegativity. So fluorine has got the highest of any element. The electronegativity is also higher the farther up the table you get. So if you're in a higher row, you have a higher electronegativity. So if I'm comparing oxygen and sulfur, I will say oxygen has got the higher electronegativity. If I am comparing nitrogen and oxygen, like I am in this molecule, oxygen has the higher electronegativity. And what that means is that oxygen in this structure will prefer to have the negative charge, the negative formal charge. But here, oxygen's got a positive formal charge. So I'm going to suspect that this structure is not the one. It is not going to be a good one compared to these other two. One of these other two might be better. Let's do the formal charges so we can see for sure. If I look at this oxygen, it's 6 minus 1, 2, 3, 4, 5, 6, 0. That looks good. The carbon here is 4 on the periodic table, minus 1, 2, 3, 4 sticks and dots is 0. Looks better yet. Okay, here the nitrogen has got 5 on the periodic table, minus 1, 2, 3, 4, 5, 6 is -1. Now, keep in mind that we have a -1 charge on this thing. So one of the charges is going to have to be a -1. We're not going to get away with getting them all to be 0 ever. But this looks much better than this. See, you've got a +1, a -2, and a 0. Here you've got a 0, a 0, and a -1. So the formal charges are better on this. And right away I can say, this structure's better than this. So I can discard that one. Now let's look at this last one. Here, the oxygen has got 6 valence electrons on the periodic table, minus 1, 2, 3, 4, 5, 6, 7 sticks and dots. So it is a -1 formal charge. Here, the carbon has got 4 valence electrons on the periodic table, minus 1, 2, 3, 4 sticks and dots. It's got a 0 formal charge. And how about the nitrogen? It's got 5 valence electrons on the periodic table, minus 1, 2, 3, 4, 5 sticks and dots, which is a 0. All right, now if I look at this one and this one, I might be tempted to say, well, they must be resonance structures of each other because they have the same set of formal charges, just moved around a little bit. But now here is something new. I know that that oxygen has got a higher electronegativity than the nitrogen. So that oxygen is going to want the negative charge. It is not going to, it's going to want the negative charge more than the nitrogen does. This structure puts a negative charge on a less electronegative atom. This one puts a negative charge on a more electronegative atom. So the whole trick, the whole thing that's new about this video is that we can say this structure is better than this one. Even though they have the same set of formal charges, the negative charge is on the more electronegative atom here. So this is the best one. So it's better than that one. So this is the only one that I'd have to report. How would I report it? Don't forget, if you've got something that's charged, put square brackets around it, and you better put that minus sign on there. I'll take a point off of that if you don't do that. So you've got to put square brackets around an ion and then put the ion charge on the outside. We know it is a -1 charge from what we have up here. Now you've got this one in the worksheet. Now it's going to work out something like the one that we just did here. But the most electronegative atom in this case is going to be the nitrogen. It's more electronegative than the sulfur. So your answer for the one that you're doing there might come out to be a little bit different. It might be one of these other structures that might be better. Give it a try.